All right, ninth graders, here we go. Number 10, when a 100 Newton bag of nails hangs motionless from a single vertical rope, how many newtons of tension are exerted in the rope? So what would that look like? We'd have our, I don't know, bag of nails, something like this. You got a rope around it that's tied up, holding it probably to some sort of ceiling or something like that. And the bag of nails has a weight of 100 newtons. So where are the forces here? Well, let's draw our bag as just a dot doing a free body diagram. And we know that that 100 newtons is the weight, and weight is always a downward force. So that's 100 newtons. Now, what else do we know? We know that it is hanging motionless. So motionless means there is no velocity. And it's not changing that velocity, which means that this must be a situation where balanced forces are in play. We know the rope is pulling up on it, so let's throw that force on here. And how much force is that providing? Well, and again, this time it's not a normal force because it's not touching a surface. This is a tension force, so just F and then I put a little T right there. So how much tension force must there be? Well, I know that the upward force of tension must equal the downward force of weight. Well, there are no other variables here, so the tension equals 100. All right, let's move on to number 11. All right, number 11. What if the bag is supported by 4 vertical ropes? Okay, so now we've got that same situation, but we've got 1, 2, 3, 4 ropes all attached to that bag of nails. And the thing is, it's like instead of 4 ropes, imagine that it's 4 different people holding on to it. So now I've got my free body diagram again, my 100 Newton force downward, again, that's the weight. But now there are 4 different forces, each represented by, or each representing one rope. So let's call it force tension 1, force tension 2, force tension 3, and force tension 4. This is probably more complicated than I need to make it, but all of these forces together are going to supply the 100 newtons that we saw in number 10. So what's the difference here? Well, the difference is they're going to each share. So each rope is going to exert 25 newtons of force because 25 plus 25 plus 25 plus 25 equals 100. All right, let's move on to number 12. An object weighs 98 newtons on Earth. How much does it weigh on planet X, where the acceleration due to gravity is 6 meters per second squared? Okay, so what do we know here? We know that the object has a weight of 98 newtons, and that's on Earth. And we know that on planet X, the acceleration due to gravity is 6 meters per second squared. So that's planet X's G, 6 meters per second squared. Well, what's our G here on Earth? Our G here on Earth is 9.8 meters per second squared. All right, so if I want to know how much this object weighs on planet X, I'll put a little X there so that I know that. I need to know something else. Well, how do we figure out what the weight is here on Earth? We do that using this equation, F equals mg, right? So if I want to know over here in planet X how much weight that has, I need to go Fg, I'll put that little X there just because I know I'm on planet X, equals the mass of the object times g on planet X. Now notice I didn't put a little X by the M thinking that there's some other mass. Remember, mass doesn't change. Mass is going to be the same no matter where you go, whether I go to planet X or planet Y or anything, any other place in the universe. So M is going to stay the same. So whatever my M is on planet X, it's going to be the same m that I have on Earth. Now, here's the thing. I don't know what m is. M on Earth is unknown. So I have to figure out m here so that I can then plug it in over on this side. So how do I figure out what m is here on Earth? Well, look at this equation right here. M equals F over G. All right, so F sub G over G, F sub G on top of G equals 98 newtons over 9.8 meters per second squared. 98 divided by 9.8 equals 10, and what is mass measured in? Kilograms. So that's our mass, and that, again, that's the mass on Earth. It's also the mass on planet X. Well, now I can take that and I can plug it in right there. And my G is 6, so that's going to come from there. Let's substitute those numbers in, and I go 10 kilograms times 6 meters per second squared equals 10 times 6 is 60 units that come across, kgm over s squared. And just a reminder, scientists don't really like to use all those units to represent one thing, so they mush them all into something called a Newton. And so that is the weight of the object on planet X. So the answer is C. All right, let's move on to number 13. All right, number 13, the little girl in the diagram below hangs at rest from the ends of a rope. How does the reading on the scale compare to her weight? Okay, so it's probably a little bit hard to see on there, but there's a little scale attached to a rope, which is attached to the main rope. So there's gonna be something there showing how much force is in that rope. And what kind of force is it? It's a tension force. All right, let's make this a little bit bigger, and instead of drawing out the person, we'll just use a dot to use a free body diagram. So what are the forces acting on the girl? Her weight. You always have weight. Weight is always a force. And there are two ropes holding her up. So the tension force of her left and the tension force of her right hand. All right, and this scale here is only going to show one of those. Well, we know that she has a certain amount of weight right here. It doesn't tell us how much weight she has, but like we've done before, the downward force, F sub G, has to equal the total upward force. And we have two upward forces here. Well, the assumption is they're both being shared equally. And so each of those forces is a tension force. Oops. And if it takes two tension forces to make her weight, then you would assume that the tension force is half of her weight. Okay? 2Ft equals F sub G, or in other words, Ft equals 1/2 times F sub G. 1/2 her weight. Again, I'm probably explaining this a lot more than you need to. I think the simple way to think about this one is, hey, if there are two ropes holding somebody up, each rope will take half of that person's weight. All right, number 14. If the force of sliding friction acting on a sliding crate is 100 newtons, how much force must be applied to maintain a constant velocity? All right, so this is kind of like the virtual lab that we did the other day. So here's our crate. And there is a force of friction as the crate slides this way. There's a force of friction, and it's sliding friction or kinetic friction. We'll call that F sub K. So the question is, how much does your applied force have to be in order for this to maintain a constant velocity? Now, that constant velocity is one of our key phrases. Why is that important? It means that if your velocity is not changing, that means your acceleration is equal to 0. If your acceleration is equal to 0, that means that the sum of all the forces, in this case F applied plus Fk, must also equal 0. The other way to think about this is if you have an acceleration of 0, you are talking about balanced forces, okay? And if you have balanced forces, that means the two forces have to be the same. All right, so if this F sub k is 100 newtons, then the applied force must also be 100 newtons. And so our answer is B. All right, number 15. What will be the net force acting on the crate? All right, so I kind of explained that one already. We already said if A equals 0, the net force, the sum of the forces, must also equal 0. That's just a true thing that you have to understand. If the acceleration of an object is 0, the net forces on the object also equals 0. All right, number 16. So what will be the acceleration? Again, I just answered this. I mean, the fact that it says in 14 that you're at a constant velocity, that means that the acceleration is 0. So it's kind of asking you the same question in different ways. All right, let's move on to number 17. How much does an astronaut weigh out in space far from any planets? And this says A, it depends on how much mass the astronaut has, B, 0 newtons, C, whatever she weighs on Earth, weight never changes, or D, there is no way of knowing. Okay, so first of all, D, there is no way of knowing is almost never the answer here, so please don't pick that one. C, whatever she weighs on Earth, weight never changes. We already talked about how that is incorrect. Weight changes all the time depending on where you go, because weight is dependent on how hard that planet or moon or asteroid or heavenly body is pulling on you. The one thing that doesn't ever change is your mass. Number A, or letter A, it says it depends on how much mass the astronaut has. That does help determine what your weight is. However, this says that you are far from any planets. And we're going to assume that this means really, really far. In fact, so far away that the effects of gravity are basically 0. Well, if there is no gravitational pull anywhere, then you don't have weight. All you have is mass. You're not going to get pulled anywhere, and so the correct answer is B. All right, and moving on to number 18. If suddenly the force of gravity of the sun stopped acting on the planets, in what kind of path would the planets move? All right, so let's say we've got our sun right here, and we have the Earth right here, and the Earth is flying around the sun. Now, why does the Earth go around the sun? It's because the sun is pulling on it. So it's actually always pulling on it toward the center of its orbit, which is the sun, right? Well, if the sun suddenly ceases to exist, then this force ceases to exist. And what direction was the planet going at this moment of time? It was going that way. So if the sun doesn't exist and that force no longer exists, the planet's just going to keep shooting off in a straight line, whichever way it was going at the time. If it was over here, it would just keep shooting straight off like that. So the correct answer here is C. And you can do that, again, with a ball on a string. You saw in the example I had in problems 1 through 9, the little practice golf ball going in the circular path and shooting straight out once it got to the end of the circle. Again, it all has to do with Newton's first law. Things keep doing what they're already doing. What is the planet already doing here? It's already going in this direction. The force of gravity is changing it constantly pulling it in that circle. But if that force of gravity vanishes, then this will just continue on because there are no forces changing it. All right?